Hello, in this video we will talk about strong acid, strong base titrations. So what is a titration? It's when you have one substance that you know the concentration of and another solution where you don't know the concentration, and then you mix them together. And usually we mix them together drop by drop. You put one in a burette, which is this thing, and then have one in a flask down here. When you do acid-base titrations, it's a neutralization reaction, is the type of reaction it's called. As you add acid, it neutralizes the base. And when it's all neutralized, before you add more acid past that, this is called the endpoint, right? When you have equal amounts according to a stoichiometric ratio of your two components. Typically it's a 1-to-1 ratio, so then that's actually equal amounts. Not always. And then you determine this endpoint by either adding an indicator, which is a molecule that changes color when you go past the endpoint, or by using a pH meter. Now, there's a titration curve, is what we call it, that describes what the pH does as you go through this titration. So you start down here when you haven't added any base. So now I'm flipping it around. So we have a strong acid in the flask, and then the base that you're adding is in the burette. So you start out here, say it's pH 1, and then you keep going, and then eventually you have this really sharp transition, and it goes through the equivalence point. And then as you keep going, it eventually curves off and kind of goes off this way. Okay, so that's the strong acid titration curve. When you did this in the first semester of chemistry, all you cared about was the equivalence point. You didn't need to plot this whole curve because it didn't really matter. You just wanted to know the volume at the equivalence point. Now, when you have a weak acid, which we'll talk about in the next video, it looks a little different. You run through this buffer region on your way to the equivalence point. The pH at the equivalence point is no longer 7, and things are just different. And so we'll get to that later. At the moment, we're just remembering how the heck to do titrations by using the content that you already know, which is the strong acid and the strong base. And so this is the mantra here. When doing a titration, the moles of, for example, H+, the moles of OH-, they're equal for an acid-base titration where the stoichiometry is 1-to-1 at the equivalence point. So now there's things we can do. We can use this relation up here to figure out the concentration of an unknown. Keep in mind if you have a polyprotic acid or a dibase, right, like barium hydroxide, BaOH2 would be a dibase, then the stoichiometry is not 1-to-1. You got to worry about that. But anyway, so we can find the concentration. We can find the molar mass. And then you can also find the pH as you go. Now, the box down at the bottom is important because it tells you that you've done all this before. We've just never gone about putting it all together. And so now we're going to put all these pieces together and figure out how to do a titration. So a little more specific, here's the equation for HCl, a strong acid, sodium hydroxide, a strong base. Here's the net ionic equation. Here's the equivalence point. We said that. Sometimes this is called the stoichiometric point. This is the same thing as the equivalence point. And then the equivalence volume is just how much volume you've added when you get there. The end point is when you stop. And your goal is that the end point, which is where the indicator changes color, your goal is that that is the same thing as the equivalence point. But often it's off by a little bit. And usually that little bit doesn't matter too much. Okay, so we're going to roll through these three types of examples. I'm going to try to do it a little fast because you've already learned this before, and this is hopefully just a refresher. All right, so we have 125 mils. We have the strong acid HCl. Don't know the concentration, but you do know the concentration of barium hydroxide and the volume of barium hydroxide that you add to reach equivalence. So we need to find the original concentration of HCl. And so here's our mantra. At the equivalence point, the moles of the OH itself that's been added is equal to the initial moles of H+ that were there in the first place. So we can calculate how much hydroxide's been added, and then we can figure out the number of moles that have been added. And then, hey, to get to concentration, you have moles over liters. Okay. So let's find the moles of hydroxide. I used barium hydroxide on purpose to show you that it doesn't have to be a 1-to-1 ratio between acid and base. So here for every mole of barium hydroxide we make 2 moles of actual hydroxide. So you have to multiply the concentration by 2 in effect. And then you multiply moles over liters by liters, and then you get moles. So this is how many moles of hydroxide we added. And then that is the same as the number of moles of H3O plus that was there in the first place. Now we need concentration. We take moles over liters, and you have concentration. Ta-da. All right. Another problem from a titration is the find the molar mass kind. So now here we have the mass of the acid that we started with. You need to know whether it's monoprotic or not. And then it goes into 25 mils of solution. And then we titrate it. So you know a concentration of base, you have a volume of base, perfect. So we want to find here both the initial concentration, just like the last problem, and now the molar mass. So our same mantra as 2 at the equivalence point, great. And then for this one, this will be true for both the acid and the base by itself, because the acid is a monoprotic acid, the base is a mono base, sodium hydroxide, so this is going to work out easy. We can calculate the hydroxide first and then solve for the H3O plus, just like before. So here's the moles of hydroxide added. Here's your concentration, multiply it by the volume, you get the number of moles of sodium hydroxide. And then the number of moles of sodium hydroxide is the same thing as the number of moles of OH, right? So these two are the same for this problem. And then we can find the moles of H3O plus. It's equal to the same thing. That's easy. And now, since this is a monoprotic acid, the number of moles of H3O plus that were neutralized is the same as the number of moles of acid. So now we know the moles of acid. All right. So then we want to get from the moles of acid to the concentration first, which is moles over liters. 25 milliliters, great. We can get this concentration. Now the molar mass, well, molar mass is grams per mole. And we measured the mass of this in the first place, and then we know the number of moles from our titration, and so then we can find the grams per mole. And so that's how you do the kind of unknown molar mass part. All right, so now the pH of a titration as you go. This is something we haven't explicitly done yet in general chemistry, but it's something you should be able to figure out from the pieces of it. All right, so you have your reaction, here's the curve. Before you start the titration, well, the pH is just from the concentration of acid, strong acid. That means the concentration of acid gives you the concentration of H+, perfect. Part way, you have to deal with the fact that you've done some of the reaction, so you've neutralized some of the acid already, and then the acid that's left over determines the pH. So you have to do the stoichiometry there in moles. When you hit the equivalence point, you've neutralized the acid and the base, you have pH 7. And then after the equivalence point, well, then your pH just depends on how much base you've added after the equivalence point. Here's another way to look at it. Hopefully this is helpful. So your strong acid is down in the flask, and you're dropping in the strong base. And, the amount of base goes along this way. So before you add the strong base, again, your pH is determined just by the acid concentration. Partway along, you have to do stoichiometry to figure out how much of your acid has been neutralized already. And then whatever acid is left over, because you're not to the equivalence point, so you still have acid around. First, you have to deal with a dilution, because you've added some solutions. You have a new volume, so you have to deal with that. Then once you find your new concentration, then concentration of the acid is equal to the concentration of H+. At the equivalence point, the stoichiometry doesn't really matter because you have pH 7 for a strong acid and a strong base, because the ions that are left over don't hydrolyze water. Once you're past the equivalence point, you have to do some stoichiometry because you added a bunch of base, but you neutralized a majority of it. But whatever base is in excess, then you find the new concentration because effectively you're diluting it. Then the pH of the excess base gives you POH, which then you can convert to pH. All right, so hopefully this is a helpful way to look at it. Okay, now let's do a titration problem where we're trying to find the pH as we go. So we have our reaction here. We have the setup. So we have 100 milliliters of a known concentration of HCl down in the flask, and we're adding in sodium hydroxide. So here we know the concentrations of both, so it's not like we're trying to find that. But we're going to try to figure out what the pH looks like as we go, according to this equivalence curve. And so I'm going to pick off 4 different points here. So first, what's the pH over here before you add any sodium hydroxide? Then what's the pH when you're kind of somewhere in the middle to the equivalence point? That's B. C will be the equivalence point, and we'll see why. And then D is up over here after you've added more base than is at the equivalence point. It's always helpful to figure out where you are first because that affects what kind of calculation you're going to do. Alright, so before we add any sodium hydroxide, for a strong acid, your pH is just determined by the concentration of the acid, and that here it's 0.1 molar, so our pH is 1. That's easy. Now, after we've added some sodium hydroxide, our pH is still determined by the amount of strong acid, but we've neutralized some of it. Right? So we started with this amount of acid, and you take the molarity of it, and you multiply by the volume in liters, and you get the number of moles. And here, the number of moles of H plus is the number of moles of acid, because it's a strong acid. Now, the hydroxide, you do the same thing. Take the concentration times the volume of it, and you get the number of moles. All right, so now let's take this. So it's a 1-to-1 mole ratio between hydroxide and hydronium, H3O plus. It also happens to be in this reaction a 1-to-1 mole ratio between HCl and NaOH. And so then how much acid is left? Well, you take the amount of acid that you started with, you subtract how much acid you reacted away, and then you get how many moles are left. If Timmy had 10 apples and you ate 3 of them, he's got 7 apples left. All right, so let's deal with these apples. So this is number of moles of acid, great. We're going to need the concentration, because when you do stoichiometry, you have to be in moles, but when you deal with pH, you need concentration. So concentration's moles per liters, but the trick here is that we now have a new total volume because we've added more solution together. And so that gives us a concentration of 0.0538. And then you take the negative log of that and you get the pH. All right, now let's find the pH after we've added 100 milliliters. And so for this problem, since the concentrations are the same, when you've added equal volumes, then you know you're at the equivalence point. If the concentrations aren't the same, then you might have to do the math to figure out where you are. All right, so here's the number of moles of acid at the start. We calculated this in the previous part. Here's the number of moles of hydroxide that we've added. And hey, these are the same. So here we're at the equivalence point. All right, I just said that. There's no H plus or OH remaining beyond what is naturally there from the auto-ionization of water. And since the sodium ion and the chloride ion are both the conjugates of strong things, they don't hydrolyze water, so the pH is 7, which comes from the auto-ionization of water, just like it always has. All right, last part. So here's the amount of acid we started with. And then now we've added this number of moles of hydroxide. New volume, more hydroxide. And so we've added more hydroxide than we had acid in the first place. So now we're past the equivalence point. And so then however much hydroxide is left over is going to drive the pH. And so we have to find what that is. So here's how much hydroxide you've added. Here's the amount of acid you had in the first place. So then here's how many hydroxides that's left over, right? If Timmy has 10 apples and you bring 12 hungry people, then there's 2 hungry people left over. And they're going to do something. And so here again, we're in moles, and then we need concentration. And so we have to divide by the new total volume, moles over liters. So here's the acid we started with, here's the base we've added. You get this molarity, right? New total volume. And so then that gives you POH, because we're dealing with hydroxide now. And then you take 14 minus POH, and you get pH. And we're at pH 12. All right, so that's all I have for this video. Just remember that you know how to do all these parts, you just have to think through how to do it, right? And a big key of that is figuring out where you are along this kind of chain, and then remembering what you got to do, right? You're probably going to have to do some stoichiometry, and then figure out what's left, and then deal with that. Cool. Well, thanks for watching.